All right, welcome to day 2 of ECS012, Media Computation. Last class, we had talked about the basics of the course. We had laid out that we're going to use P5JS and an eye on the theoretical side and the practice side of media computation together to inform ourselves on this idea of computation and how we can use it as a medium for expression, creation, art, analysis, whatever you want to use it for. This class is a great place to get started. We also had a lab this morning and on Tuesday. That Tuesday 8 a.m. lab was really cold, and the doors didn't open until right at 8, so it was a little rough. Thank you all for bearing with that. Hopefully, we've sent the correct emails to get the appropriate changes to make the experience a little better. But the lab success rate was quite high. Almost everyone completed the lab on time, even with us having to do quite a bit of explanation. Most labs will be much less preamble and much less lecture and much more you doing the thing, doing the practice that is part of the lab. So we will make that transition, but we had to get started first. Today, we're going to continue our conversation into readability, color, and transformations. Some basic capacities that we're going to need to move forward. Now, overall in the class, as you can see from the schedule, we will incrementally integrate new programming concepts into what we know. We'll show why these concepts exist and how we use them. And we'll have a lot of examples. The labs will feature ways to get your hands on. It just die already? Okay, I was worried about this. Yeah. And there are new batteries, which is why I have a handheld mic backup. All right. I guess I have plenty of M's and C's in my name for this, right? Great. So, check. Okay, it is working. I had just a moment there. So we will integrate these ideas, and including today, we will start putting a more fine-grained detail. You're going to see a lot more code than we did last time and a lot less syllabus for sure. And at the end of the class, we will wrap up with assignment 1, which will be due a week from today. All right, so that was a bit of bookkeeping. I guess a little bit more. Canvas was a bit of a mess during the transition, the automated transition from last year to this year, which also included a non-automated portion of a human at Canvas actually smushing all 4 sections together. That wreaked havoc on the schedule and the assignments. So you may have noticed you had a whole bunch of overdue work from 2023 that has now been corrected. And there are a few things I need to tweak about the assignments, including changing them from submission forms to no submission forms. So that is in process, but most of it's already done. It should be a much cleaner Canvas experience for you now. Let me know if you see any rough edges and I'll fix them up. All right. Drawing practice. So we have used now you have used Rect. You've used Rect a few times. You've used fill. We've talked about colors. We've introduced this idea of numbers and strings. We've talked about commands. And in one of the sections, we even talked about how computers read commands. How many of you have made trees from sentences with subject, object, verbs? Have you all done this? Made tree structures from the basic syntax of English? And maybe some other languages too? Yeah. Well, that's exactly how compilers and interpreters, which are the terms for the for the programs that read your code. They make syntax trees out of your code. And so we see here, like this ellipse call, which we'll talk about and you'll use for exercise 1, it'll break out this left portion as the name a function name. And then it will see this left parentheses and put that in another leaf in the tree called a left paren. And then it'll have argument 1, comma, each one of those are leaves, argument 2, comma, argument 3, comma, argument 4, and then left paren, and then statement in semicolon. It'll parse all those out into a tree. And we do that, and it knows sort of what tokens or what letters to look for next. And it treats white space as interstitial space, as buffer space. You can have tabs or any number of tabs or any number of spaces when there are spaces in programs. It's not good practice to have a whole bunch of tabs and spaces, but you can. The interpreter compilers don't really care. For the most part, there are some white space dependent languages such as Python, but not for this class. So it knows what's coming next. It can read your code and turn it into a tree and then look at that tree and make the appropriate actions, which is why we have things like camel case, like some we talked about in some of the labs, where you have rect and then capital M mode. So we take things that are multi-word and we smush them together and capitalize every subsequent word. That's a programming naming convention. Each programming language has their own sets of conventions, but this camel case, or humps in the word sequences for each individual letter, or for each initial letter in each word, is a very popular and common one that you will see a lot. We'll use it quite extensively for this class. But if there were white spaces in between each word, it would make the interpreter and compiler's ability to make a tree much more difficult, which is why that exists. All right, so rect mode. This lets us determine what those 4 parameters mean, those 4 numbers that you put in rect. So for lab, what did the first 2 numbers mean? Yeah, what? Position. Exactly. What about the second 2 numbers? Dimensions, width and height. Yeah. Now, you notice I talked about in the first class, the first 2 being the top left corner and the bottom 2 being the bottom right corner. Well, that is one of the modes, and it used to be the default mode. So apologies for getting them confused. The default mode is as we used in the lab, with height and width being the 3rd and 4th parameter. Now, what about that red box in the middle? Was that the toughest box to find the place for? Yeah. Why is it? Why was it tough? Yeah.
You have to mentally calculate where the offset of the corners relative to center.
Exactly. You had to find where the center was and make sure the center of the box was in the center of the canvas. Now, you could have used rect mode center, and the first 2 coordinates would have then been the center of the rectangle, as opposed to sort of like that top left point. And then the width and height would sort of like expand around that center. Right? So this is why we're talking about rect modes and ellipse modes. They're very handy for doing specific tasks. One mode is hard. It makes one part of life difficult and one part of life easy. And the other mode makes some tasks much easier than others. And so part of learning how to program, learning how to think in this way allows you to choose which mode is best for any given task to make your life a little easier. Ellipse. That's how we draw circles and circle-like things. The first 2 arguments are the center of the circle, of the ellipse. And the 3rd and 4th arguments are the width and height. If the width and height are the same value, you get a circle, a standard circle. If like the width is bigger than the height, you get a smushed circle. Like as if you put something heavy down on it. And then if the height is bigger than the width, you get something that looks like it's been squished from the sides and is more up and down than it is left and right. So after you've dealt with rectangle, I bet you have a pretty good idea of how to conceptualize ellipse. So here are some examples. I'll send this out after class, but you can draw squares, circles. You can draw circles over squares and make some cool effects like this thing that looks like it has a cutout in it, but all that it is a circle, a white circle drawn on top of a black square. A little aside about writing clean code. You're just getting started. Now is the time to build good habits. I love these inherited slides. They're kind of funny. Computers are a bit like uptight grammar teachers. If everything is not stated precisely, they will not understand you. And then we talked about, we had this a little bit last class about how computers are kind of stupid in a lot of ways compared to humans. Designing computers and doing things with them takes a lot of brilliant human insight. And they're really good at math. They're really good at crunching numbers quickly. But it's difficult to make them understand ambiguity. Even with our deepest of neural networks, ambiguity is still something that machines will struggle with. It is still a mystery as to how our context-rich, experience-laden human brains actually have this round, common-sense thinking capability. So far, we have not captured that in an algorithm. Who knows if we ever will? But for our lives, for our current future of computational thinking, it's still very difficult. I mean, you've probably all tried to answer some questions with a large language model, and it maybe gives you a little bit of the answer. It gives you the normative space of answers. There's still a lot it won't do for you. Like, you could give it that box and square diagram from Lab 1 and say, hey, can you make the commands to draw this? And it probably will fall flat on its face. I haven't tried it. Maybe I will. Semicolons traditionally end a command. They're a way to say, hey, I'm done with this right. Please take care of it. Now, in many programming languages, the semicolon is required. JavaScript is a language in transition. It's a language that is maturing. It is a language that is rethinking old standards and integrating new ones. And one of those new standards is, why do we even need this semicolon thing? So semicolons are actually optional. And for this class, I will support whether you want to use semicolons or not, but be consistent. If you use semicolons in one place and not in others, that is not good. Consistency and cleanly and having clean code that is easy to understand is important, particularly as you're growing and learning in this area. So we'll give you some style guides and further guidance, but as far as this is concerned, pick your poison. Now, there are lots of things that we use here that are more rare in English. We do use parentheses in English, but we use them, I think, a little more extensively in computer science. So left paren and right paren, they're usually used for lists of things, particularly argument lists for commands. They're also used in mathematics in much the way, or in arithmetic, much the same way you've learned in all of your math classes. We'll go over some math operators and how it's slightly different than what you know from geometry or algebra. Now, we get to use these curly brace operators. All right, how many of you have actually used that button on your keyboard? What have you used it for?
Code citation.
Yeah, code citations. Yeah, so if you've used it for code, obviously, yeah, that's of course. Did you have your hand up?
I just used it because I thought that looked cool when I was a kid.
Right. You use it because it's rad. You often use it for ways that distinguish the text you're writing from other parts. Like, hey, team member 4, you need to fill in this paragraph on the fall of Rome, or else, right? This is often a common use case in English in our common essay and writing lives with curly braces. We use it as a catch-all, as a thing that's different. But for code, it denotes something very specific. In JavaScript, it denotes blocks of code. So it's not very handy to have all of your code in one flat structure. We need a way to group things together in meaningful chunks. This is what those curly brace operators do. So we had that function setup and function draw. Those curly braces say what's inside of those? What entails setup? What is the body of the thing called setup? Same way with draw. What's inside the body of draw? Everything inside its subsequent curly brace pair, is associated with that call, with that function, with that command. We'll disambiguate commands versus functions when we learn more about functions. And then we have the square brackets. How many of you used square brackets before? Okay, what context? I'm curious, just anyone.
Code.
Yeah, code?
When you skip over a part of a quote, you can do the square brackets and then the ellipses in the middle.
Oh, yeah, square brackets and ellipses for quotes, of course, yes.
Parentheses within parentheses.
Oh, okay. So you use it to disambiguate the layers of the onion, that is your parenthetical statements, like an ogre. Okay, yeah.
When you're also in quotation, when you're when the actual quote is like a pronoun, but then you need to specify who's saying it, and so you put the name with the brackets.
Yeah, so it has this extra informational quality, this contextual enhancement quality to it. Yeah.
Like separating, like also parentheses and parentheses, but in math when you're writing it on a computer.
Yeah. So math is definitely uses the square brackets a little more. For us, we're going to use them for arrays. So chunks of numbers or strings that are essentially sequenced together. And we will learn a lot more about that, particularly in week 5 or 6. It'll be a very powerful thing for us. It'll be something that hopefully you will see sort of like the power of the ability for a computer to do a lot of things very quickly. These arrays help unlock that power substantially. All right, white space we talked about. Comments, we sort of left implicit. There are 2 types of comments in JavaScript. There are single line comments, so 2 4/, that is not to be confused with the backslash. It is not the one above enter. It is the one to the left of the right shift. These 4/, if you put 2 of them in a row, anything on that line or after will be ignored by the interpreter. This is really handy because now you can start writing yourself notes. Like I've left notes for you inside of the sketches. This is where you can put in reminders to yourself. You can sketch out what you want things to do before you actually write the code without making your code break. It's quite handy. I encourage you to comment a lot. The more you comment your code, particularly when we're grading, the more we'll understand what you're thinking, and the more likely we are to make the grade better because we know more what's in your head. There's also a multi-line comment, so / asterisk or star, the lovely shift of 8. You put a / in a star, everything will be ignored by the interpreter until it sees another star, then /. So you can make huge blocks of comments with this. Luckily, it will turn gray. So I have it in gray in the slides. That's roughly the shade of gray that you will see inside of the openprocessing.org editor when you use those comments. Now, indenting is really important for code readability. So we talked about using those curly braces to denote groups of code, right? But a lot of times you have groups within groups. And then you have this implicit group at the very top. That if you put nothing in a file, the very first line there's implicitly some curly braces around it. So when we do function setup and we have those curly braces there, notice that we indent to denote things that are inside of that scope, of that function body. And then we'll see later as we get into iteration or conditional constructs, they also have bodies. And so now you have these scopes inside of scopes or bodies inside of bodies, and to help you make sense of it as a person looking at a bunch of text on a screen, we use indent to help out. Now, luckily, if you look in the options of your editor, there is a clean up your code command that will do a lot of this work for you, that will help you keep your code clean, that will indent things for you. I recommend you use it liberally. And we'll cover that in next lab, I believe. Color. We talked a bit about color earlier. What are the primary colors?
Red, blue, green.
Red, blue, green. Anyone have a different take? Magenta, cyan, yellow. Was that what you were all? Yeah.
No, it's red, green, and blue.
Red, green, and blue. You're right. You're right. It's not. I always get this mixed up because Notorious RBG, right? But it is red, green, blue. Anyone else?
Red, yellow, blue. Red, yellow, blue.
Red, yellow, blue. Yeah. There's a whole bunch of these different like primary color schemes that we focus around, but by far the most common one is the red, green, blue. Who doesn't have their sweet gaming chair with their gaming laptop with RBG lights all over it, right? Or Christmas lights. Now Christmas lights come in so many lovely colors that you can change on demand. There are subtractive primaries, and these are used for printing. Just the way ink works, having cyan, magenta, and yellow is very handy for color reproduction on paper. And then we have the additive primaries, red, green, and blue. And it's used with mixing light, and particularly useful for displays, which I believe is why it is very popular and well known now, since displays are where we commonly use, where the every person comes into contact with specifying color computationally or on screens. MS Paint, GIFs. And there's lots of ways to set colors. So this is from OpenGL, which is a very high-end sophisticated library for making computer graphics. Now here, you set colors. So GL3F, that's setting a color for red, green, and blue, where each one of the R, G, and B values are decimal or floating point values. Don't need to remember that right away. I'm just explaining what's going on here. It's the function has the argument parameter is sort of like built into the function name. So 3F means it takes 3 decimal things. Now, you can see here how these add together. Red plus green equals yellow, green plus blue is cyan, red plus blue is magenta, red, green, and blue is white. I'm sure you've all encountered this extensively, so we'll not beleaguer this point, but it's pretty to see it all laid out there. Now, a more formal way to look at it is the color cube, where you have each corner being one of those additive maximalist spaces, where you have full white being the first edge of the cube, and black being the opposite corner, and then green, cyan, blue. So each one of the primary colors that are denoted by ones in their own category are at corners, and then you can go to the other corners and see the additions together. And you may have seen like the hex color picker. How many of you have encountered a hex color picker before? Right? This, all that you're seeing is that cube at an angle from the front, projected into like 2 dimensions instead of 3. That's what it is. And if you check the shade button, where you can change the color to be more white or more black, all of that is pushing you through the cube, taking different slices out of the cube. right? So I think it's quite interesting to lay this out in the way that, you know, folks have thought about this in the past. But it's actually way more complex than a cube. These are, so what we're seeing here in this color spectrum here, this is what the human eye can see. We are creatures that grew up in forests near plants, you know, surviving on tundras and whatever, or middle you know, geography of northern Africa, tundras. So we have evolved a lot of perceptual capabilities to see green in various shades of green. We're really good at green. We're not so good at red and blue. Right? So you can see how much space we have in green and how little we have in red and blue. It turns out that reproducing this level of color, particularly green, has been problematic in both print and in displays. So what we see here are various areas within that human perceptual space of colors that can be reproduced by various technologies. So computer monitors, and they vary quite a bit, are the triangle. Right? They get pretty close to blue, not so close to red. They're really bad at green. And then we have what CMYK can represent, and then what the official Pantone color spectrum can represent. Right, and you can see here it's a little light compared. So now you can see, I guess, where the white is here, so you can see what the computer monitors can see out of this particular spectrum. And now you can like take a look and see, like, oh, look, it's really good at these hot colors, these reddish zones. A little bit of blue and a little more green. But that's, you know, if you compare it to what we can perceive with our eyes, it's still quite paltry. Here are various color gamut specifications compared to the human perceptual spectrum. Now, these are what could conceptually be represented, but we still don't have the display technologies to handle them. This is just, there is a space of representation where you could send that representation to some sort of output, display, print, whatever, and if it can produce that color, you know, you're good. There's it at least can represent the color space. So we actually don't have a lot of nuance, even in just representing that huge amount of green that we can see. Particularly when the green goes a little more towards the blue part of the spectrum. It's very, very difficult for us to even capture that, let alone represent it on a screen or on print. I think this is pretty fascinating, right? There's still so much about the human perceptual system that is still being discovered. And so there are various values here, like the famous Adobe RGB 1998 spectrum. Some of you may have heard of this, Profoto RGB, which captures a lot, including, I think pretty hilariously, blues that we can't see. It goes ultraviolet. So color gamuts are interesting, particularly when you can visualize them in 3D. Just like that color hex, it really is a higher dimensional space than something flat. And so you get a little more nuance of what these color gamuts can represent. And you see the big slice out of green that we just don't have a good idea to get through or get past. But it does really good with red. Color decode. So we talked a little bit about color decode earlier, but I want to get us started here thinking about ways to handle some other drawing that we can use with colors, particularly line. So line is pretty handy. Start X, start Y, index, end Y, drawing a line between 2 points. We'll use that in assignment 1. And we've talked about how the name indicates the name of the command, and then it has an argument list. So color and processing, in which P5 inherits processing's ideas. Colors can be defined in a tuple, red, green, and blue. Values between 0 and 255. 0 is none of that color. 255 is max of that color. So 255, 255, 255 is... Yes, white, yes. And 000 is... black. Thank you. So we know this, and we were using grayscale last class in grayscale in the lab. Basically what that does is it takes one value and just like repeats it 3 times. So if you want to have any, like if you want a quick formula for gray in RGB, it's when all 3 values are equal and not 0 and not 255. And we have some examples: bright red, bright yellow, dull yellow, mid-gray. Can draw a blue, not all the way blue, but just mostly blue, like an electric blue. But did you realize there was a 4th parameter to fill? A 4th parameter for colors. I bet you did, because I bet you used it before. It's the alpha channel, or the transparency value. 0 is transparent. 255 is fully opaque. So 0 of it or all of it. And the default value is opaque, 255. This will be handy on challenge 3 of assignment 1. But why 255? Well, we all know computers represent data as combinations of bits. And a bit can either be 0 or 1, off or on, true or false. Numbers can be represented by multiple bits. How many of this is like review for you? Have you all done the powers of 2 into binary representations? I know the computer scientists are like, yes, of course, and people are raising their hands, but I get a lot of people who are not even looking me in the eye. So, all right, so here is a little table where we combine a bunch of 0 and 1 values together to interpret them as a set of whole numbers, as a set of integers. So let's say we have all of the bits being 0, we'll get 0 out. If we have this rightmost bit at 1 and the others at 0, it will mean 1. But if we have this at 0, we have this, and the second bit is 1 and the third bit is 0, it's interpreted as 2. Right? So each of these are subsequently higher powers of 2, and then you just add all those values together. And that's how we get binary representation of integer values. 111 is 7. Bits, bytes, and pretzels. So computer hardware is designed to work with particular numbers or group sizes of bits. 4, 8, 16, 32, the Nintendo 64. Right? So for a while there, the bit count of the processor, or the size of the registers that you would use to interface with the graphics hardware, the sound hardware, was a big selling point. We had 8-bit games for the NES, and then we had 16-bit games. Does anyone know a 16-bit console? Yeah?
Sega Genesis.
Sega Genesis. Anybody get another? Yeah.
I'm not gonna help you.
Okay. Yeah.
Super Nintendo?
The Super Nintendo, one of my favorites. Yes. Right? And then 32 bits was the next generation, including most of the Nintendo 64. But there were aspects that are of 64-bit processing that moved into the console market. Now, most of the processors that you have are 64-bit processors. For a very long time, 32-bit was the big standard. But it turns out we wanted file sizes and hard drives that were bigger than 4 gigabytes. So we needed bigger bit registers. Particularly now when, like, geez, what I downloaded Call of Duty, the latest Modern Warfare, or no, it was COD Block 6, and it was like over 300 gigabytes, right? These are massive now, and now we need this large 64-bit space of addressing particular values, since we have to be able to pick out any one of those bits within those like large gigabyte file ranges. We have to be able to say, hey, we want this particular bit, and we have to be able to address all of those particular bits. So we need this sort of register or computer group size space that's big enough to have enough one of those powers of twos to pick out any one of those bits in this space of billions and trillions and quadrillions. Eight bytes is a bit. Anyone know what a nibble is? 4 bytes, or 4 bits. What about a word? Word 16. What about this is gonna be tricky, a double word? 32. Not so tricky. A pretzel is 64. So 1 byte can hold, since it is 8 bits, to the 8th values, 0 to 255. This is why all of our values for red, green, and blue are 0 to 255, because they can be represented with 1 byte. Now, if we have 4 bytes in a row, 1 for red, 1 for green, 1 for blue, 1 for alpha, all of a sudden we have a 32-bit color value. Right? That's better than the Super Nintendo. That's a lot of space we can represent. And it's typically good enough for most situations. Now, we do have 64-bit color values and 128-bit color values. But as you can see, we have a hard enough time reproducing the human color gamut and a hard enough time representing those sets of greens in reasonable ways that, it's hard to need more than, billions of individual color values. And so here is what the color values can look like. If all the bits in that row, in the top darker orange row, are 0, we'll get 0, or black, or none of red, or none of blue and none of green, or fully transparent. And if they're all 1, it'll be 255, or all white, all red, maximum green, maximum blue, fully opaque. All right. We've, I think, thoroughly went through colors and representation. It is very likely that those types of things will be in the midterm, so glad you were taking notes and paying attention, being diligent. Let's talk about translate. So translate moves the origin. It moves where 0, 0 is. Come on in, have a seat. 0, 0, by default, is at the top left. As we've discussed multiple times, we also know that we have an inverted y-axis where counting up in y takes you down. Higher y values go down, lower y values go up. You could also be negative x and y, which will push you off the edge of the screen. And so you won't see it on the screen. You could also go past the edge of the screen, past the edge of your canvas with higher x and y values and also not see what you're drawing. Do you need to have a seat? Feel free to move, folks. Okay, all right. Now, translate is very handy for us because 0, 0 is meaningful. We don't want to do a whole bunch of math every time we want to place something complex. So instead of doing a bunch of math to find where the left-hand value of this large square object should be, we can simply move where 0 is to match it. That way, let's say you have a fancy set of rectangles and squares that you've made to have the perfect shape that you like, and you started that whole construct at 100, 100. Let's say you want to draw it again somewhere else. Instead of changing all those numbers, you can change where 0, 0 is, and it will still have that relative according to where 0, 0 is now offset. So you can draw it somewhere else without doing a whole bunch of new code, without, in your mind, as a human, calculating a whole bunch of new values. So translate's really important. And just like fill and stroke, rect mode, ellipse mode, line mode, it's state that persists. When you change the origin, it will last until you change it again. So it's transformation state. So to be explicit, and I know this is probably common sense for a lot of you already, we are drawing on a grid where each individual cell is a pixel. And that's our granular level of resolution. So when we translate, 0, 0 is here, the very top left. If we translate it by 10, 10, well, let's make it 2, 2 so I can reasonably do this. 0, 0 is now here. And what was 0, 0 before is now -2, -2. So now we will draw 0, 0 relative to here. So all of your x, y positions in your rects will now be offset to account for the new origin. Now we have rotate. This is where you spin things around. So it takes an angle, which is in radians by default. But fear not, a lot of us think more intuitively in degrees, and you get to pick which you want to use. In setup, if you don't like angle mode being in radians, you can set angle mode 2 degrees. And so you can give it your normal degree values that most folks are used to. Or 90 degrees is a right angle, etc. 360 is the full circle. So this is handy. So we can rotate things. We can move them around, spin, but there's a catch. It has a pivot point. So if you want to rotate something, it has to rotate around some point. That point, when you use rotate, is the origin. So let's say you want to rotate a rectangle into a diamond and offset it by 45 degrees. And you draw that rectangle at 10, 10. Its center is at 10, 10. If you rotate it without translating, what will happen? It'll actually move like it'll look like it's moving around a circle because you're rotating at that 0, 0 point. It's at 10, 10. So it's like shifting that piece of paper over. So if you wanted to rotate this square that's at 10, 10, you want to just turn it, you have to know where the middle point of the turning should be. So you would want to translate to 10, 10 so the origin 0, 0 is now right in the middle of that rectangle. And then you can rotate it by 45 degrees. And now you made a diamond. And it's good to think of this type of transformation, rotations, translations. Just like stroke and fill, these are states. They are setting different modes, setting different ways the machine interprets what the code interprets what you do next. It's like dipping or picking up a colored pencil, a red colored pencil, and using it. If you want to switch to a blue colored pencil, you better pick up the blue colored pencil and then use it next. Or dip your brush in a different color of paints. But this actually gives us a lot of power. Keeping this context around is very handy for us. And you can pair a bunch of translates and rotations together. If you translate a 10, 10, and then you do another 5, 5, it is now 15, 15 from that original origin. So they can compound. Let's do a little example. So what we have here on the right is our result, what we want. So we want this rectangle to have its top left corner at the coordinate 3, 2, pixel 3, 2, x of 3, y of 2. What will we put in this translate call at the top to make this blue rectangle drawn at 0, 0 on this command? What will we put in translate to get the result on the right? Yeah.
Would y be 1?
Not quite. But no, you're on the right track.
Would you just put 3 and 2?
You just put 3 and 2 there. So we want to draw this at 0, 0, but we want the outcome to be, like 3, 2 in the window pixel space. So we're just going to move that origin down a little bit. We're going to move it 3 pixels to the right and 2 pixels down. Good job. All right. Let's say it's already translated so that origin is at 100, 100. What would we put in this translate call to make it appear at 3, 2? Do we have hands? All right, give Popa I see your hand. I would just give folks a minute to grok. I see a lot of mouths going. All right, what do you got? Sorry? Nope, because then you'll be drawing the top left corner at 103, 102, according from the original coordinates. Yeah.
-97, -98.
-97, -98, right? So the result of subtracting 97 from 100 is 3, and the result from subtracting 98 from 100 is 2. So we're back at our 3, 2. Does that make sense, everyone? Are we disambiguating, demystifying this process? It's important because we're going to need it. All right. Now we have this rect call, 200, 100, 100, 200, and we want the rectangle to be also at 3, 2. What would our translate be? Yeah.
Is it -197 and -98?
Yes, exactly. -197, -98. We're just doing simple arithmetic here, which I know I would hate doing on the fly. Good job. But when you're sitting down and doing your own math, making your own things, it's a little different, a little easier to write things down and play with the graph paper, perhaps. All right, here's the tricky one. We want to translate and we want to rotate. So you can either ignore radians. So what we want is to give degrees. So radians is a function that will take degrees and turn it into radians, which is what the default uses. You can also ignore this, pretend that there is a degree value here and that you've set angle mode to degrees. All right, so the trick here is that we want this original 100, 200 aspect ratio. So we want a 100 wide and 200 tall. But what we have drawn here is something 200 wide and 100 tall. So we want something that's 100, 200 at 3, 2. What combination of translation and rotation do we need? And I should note that the rotation is clockwise. I love everybody's like doing little things with their fingers, like they're casting tiny magic spells. Yeah.
Is it 3, 2?
So close.
Okay.
Yeah, you're so close. It is 3, 2. 90 is almost there. You're just pointed, now it's pointing in the wrong direction.
Okay. I'll listen.
Yeah, I think you've got it. I think you would be able to fix it. So we know translates 3, 2, and we know 90 is conceptually close. Yes.
270.
270, exactly. 3, 2 is the translate, and we rotate 270. So we're spinning it around 270 degrees. All right, have I made your brains hurt yet? That's okay. We can play with this in code and make it a little easier so we don't have to map everything in our brains. So commands like rotate and translate, they set state that affects all future drawing commands, just like fill and stroke. This is called the current transformation state, as opposed to current color or drawing states. These commands act relative to the current state. So calling translate followed by a translate is, so if you call translate 100, 0, followed by translate 50, 0, it's the exact same as calling a single translate 150, 0. Rotation, however, is not the same. Rotation really depends on the order. Now, here's something that's going to be maybe a little challenging, but it will be a capability that will be critical to us going forward. That is push and pop. All of these are states. So what push does is it says, okay, save the state that we are currently in just right before the push is called. And push gives us another state to work with, another state on a state stack. And that way we can do all this rotation, translation, muck with things as much as we want. And then we can call pop. And what pop does is it gets rid of that one we've been using and goes back to the one that it goes back to the state right before we pushed. Right, so this is pretty handy. So we have this, I don't know, we've made a really sweet looking capybara out of ellipses. Right, and we want to draw it twice. We want it to have a little friend. Maybe we want to have a big capybara and a tiny capybara. Maybe put the tiny one on the big one's back. So we have all the drawing commands for the cappy. We started at 0, 0. Now we can copy all of those rects and ellipses or whatever we use to draw the cappy. We can then call push and then say, hey, okay, now we want the origin to be just above the adult cappy's back. And now we want to use another transformation command called scale and scale it down. Maybe we want to rotate a little bit so it looks like it's climbing the back. And so we can draw that cappy there. But let's say we want a third cappy. So then we can push pop. We can call pop and go back to the original coordinate system with none of our translations or rotations and make another one. So where do we want this other cappy? Maybe we want a medium cappy that is looking at the adult cappy in the face. So it's shifted over, I guess, to the right a little bit of the adult cappy and then flipped around. So now we can put in those commands. We can use a skew or rotate and a flip. We can scale and translate just like we did before. But we're back at the original coordinate system, so it makes sense. We can do another push and another pop. So now we can start drawing things. So all these cappies, like all the code for those cappies is the exact same. The only thing that changed around it was the coordinate system and the translation states. So we're starting to get a little tool here for being able to reuse our code, saving ourselves a lot of time and energy. Instead of refiguring out where all those coordinates are for a small cappy versus a large cappy, we can just use the large cappy and change it. So it's quite handy. This push and pop will be very handy for you to learn. It's also a little mind-bending, but that's good for you, right? So this is a basic way of how you do it. You push to save that default state, change a whole bunch of things, and when you want that default state back, you pop. Okay. I think that was enough for right now. We've went over colors. We've been over bits and bytes and pretzels. We've went over a lot of concepts around color. We still have 15 minutes, or we still have 25 minutes left. Let's talk about exercise 1, or assignment 1. All right, so if you go to Canvas, you'll see assignments. You'll see that things are a little more cleaned up at the bottom. I guess I get to see a lot of things that you don't see now, since I have special privileges as the instructor. You'll see assignment 1 called Basic Drawing. And you'll see a bunch of links here. So assignment 1 is broken into 4 parts. It is worth 5% of your total grade, but we are grading it on a 100-point scale. So every 20 points that you have on the assignment will be 1 point of final grade, right? So it's normalized. Challenge 1 and 2 are worth 30 points of that 100 each, and challenge 3 is worth 40 points, and challenge 4 is a bonus point project. So if you lose any points on the first 3 challenges, and you can make up to 15 of those points back with challenge 4. So these challenges work just the same as the labs. I have a base sketch for you to fork/copy, and you have to add it to the particular category. Let's take a look. So this is challenge 1. Pardon me as I log in. So you should be able just to click right here and go right to the category for that portion of the assignment. There we are. Assignment 1, challenge 1. So we have some preamble. In this assignment, you will write code to create 3 or 4 different images. Coding images in this way is not the most effective use of processing, nor is it probably the best way to create simple images. A drawing program is well suited for that. However, this is an exercise that you can do with relatively little knowledge of P5.js, and is a great way to become familiar with this programming environment, basic drawing commands, and working with the pixel grid. It will sharpen your skills, so you are ready to go when we really start tapping into the power of programming. All right. So a small portion of your grade will be your code looking clean, doing the auto format and cleanup. So all the things within the function bodies align. You have one code statement on each line. Things are clear and readable. You have comments when things get rough. All right. So looking at the lab, we have a whole lot of submissions, right? And it's kind of hard to pick out the one that you need to fork. This is why I gave you a link to it directly right here. So this is challenge 1, featuring the ellipse command. And we're all Elsa. We're going to draw a snowman. So using ellipses, I want you to approximate the snowman image. I've already given you the pixel size. I'm not sure why it's not loading, but it is a 400 by 800 image. Taller than it is wide. You can use ellipses in different orders and stroke and fill of different colors, or really just fill of different colors with the same stroke to make a snowman. And I give you a link to the reference for ellipse at p5js.org. Hey, look, it's pledge drive time. Oops. I didn't mean to actually click that. I meant to click the X. They make the X's very tiny to click, right? So it's kind of how we talked about X and Y with the width and height value. X and Y is the position of the center of the ellipse, and W and H are the width and height of it along its major axes. And I give you just a little bit of code to start with. Challenge 2. A little bit of the same preamble. Here, we're going to use rect and translate. We're going to use push and pop. The goal here is for you to draw this little house-looking object with rectangles first. So this one is rectangles. And then we want you to push, draw the rectangle, pop. Then below it, we want you to draw the same icon, but with line instead of rect. And here's a little code sketch to help you out. Push, do your transformations, draw a rectangle, pop, draw your next rectangle, because you're going to have to draw this first one, skinny one, and then you're going to have to translate and rotate appropriately to draw the angled ones. And then you'll have to do the same thing with, you have to draw it with lines. And so you're going to discover the difference between those two. And here's a bunch of documentation on line, push, pop, transformation, or translate, and rotate. All right, here's challenge 3. I want you to recreate this image. Let's see if it'll load so we can see it in total. Or not. That's fine too. So we're basically drawing a Pac-Man-like object eating power pill-like things, eating pill-like things. So you're going to need to use arc for this, a third command, to be able to draw a circle with a cutout. And you'll be using rect to draw the gray pills. You'll be using an ellipse to draw this eye, and you'll be using a rect to draw the purple ground. But notice here that Pac-Man is a little translucent. You can see through Pac-Man. Pac-Man has a little bit of transparency. So you're going to have to use that third value of color, the alpha color, the alpha channel, to denote that Pac-Man's body is transparent. And finally, we have our bonus point challenge 4. I want you to draw something. You get to pick. If it's something that's just like a simple square, not very complex, you won't get many bonus points, if any. But the more interesting and the more complex you go, the more points you will get. So you can have a little fun. A little bit in the context of an assignment. I know some of you have already started just like drawing things. Like several people have done it during the labs, finished early, and then started poking around. Maybe even continue that poking around and use it for the assignment. You don't have to waste that energy. Get points for it. All right. So there is a naming convention I want you to use. And you can see that on each one of these. So we'll just go to exercise 1 here. And if you scroll down on this category, hey, look at all these already. I want you to name your sketch, kind of like we did for the labs. They're already called, like, assignment 1, challenge 1 is A1C1. So I want you to keep that A1C1 prefix and then put dash your name. And if I were to do this myself, I would do A1C1 dash Joshua McCoy. And then I would set the privacy options to teacher only. I don't think you have to do that because all these categories are set as exam categories. And when you make a copy or when you submit a sketch to it, it automatically sets it so that only the instruction team can see it. But better be safe. All right, any questions on assignment 1? Yes.
For the snow, is it like, do you have to perfectly match up? Because like, it's kind of like almost like not to scale type of thing.
Yeah, the snowman, you can get close. Okay. Like we will accept close approximations. for the snowman and for the Pac-Man, since we didn't give you exact values. And it's much harder to infer what the exact values are than the squares we were using for exercise 1. Our goal here isn't, we want you to get, precise. We want you to get close, but it doesn't have to be perfect. We're much more interested that you know how to use the commands and write the JavaScript and P5.js that would entail a decent solution to the problems. Now, if your snowman's only like half the height of the original snowman, that's going to be a little bit of a problem. It should be like within like 10% of its dimensions. I think you all can handle that. That's enough that eyeballing should be sufficient. Give you enough wiggle room. Any other questions? It's due a week from today at midnight. The submission process is just like the lab submission process. We're going to grade whatever you have uploaded and saved to each one of these 4 categories for the assignment. All right. So I hope you all can get started on these. I will announce some office hours soon. We'll have some likely on Wednesdays between lab and class. I think will be the time block that I will have some availability. I may have labs perhaps later on Tuesdays. I will try to find a formulated decent survey and send it out to you to see, given a set of office hours options, where we want persistent office hours. And also, we should note that there is a policy in our syllabus that is inherited that I promise to keep in the class, where we will not give instructional help on the 24 hours before the assignment is due for fairness reasons. So make sure you get started a little early and ask your questions a little early. Actually put it inside there. Here's a little bit of code. You won't understand all this yet. This is actually using the fancy things we call variables. Names that hold values, labels that hold values. We'll get into that. But here's a setup with a fill color and a draw color. And you'll see there's some things here that makes it go. But what we're doing here is we're using rect with a whole bunch of parameters. 8 parameter rect. Where's my master? There it is. It does this. This is just a simple animation of the corners, I guess. Why is this projector going like way down? Here, do you want to see the rest? It's on my hand. There we go. All right, so simple animation. Just some things to stoke your imagination a little bit. And then we have this one with some shades with various colors. And a lot of pushes and pops. Push, pop, and scale. We're changing the scale of things, like how big or small it is. We can reduce its size by 50%. We can squish it. This is actually keeping the X scale the same, but changing the Y scale. What do you think that does? Yeah, you can either stretch it by making that Y scale bigger than 1 or squish it by making it less than 1. And we're doing a bunch of pushing. So we're scaling on top of scaling on top of scaling on top of scaling. And then doing a whole bunch of pops. All right, what's a mental image? We're doing a lot of these ellipses with a lot of these shades. I want you to just think for a minute, like what you think this output would be. What are we going to get here? And just note that fill is turned off. There is no middle. But we're using a bunch of colors. Let's see. Do you think it was this? took a chartreuse-based color progression and mapped it to the various scale downs. And each time we scale down a little more until we get to this chartreuse-ish melon, this green onion cut in half, this eco-friendly Eye of Sauron. So these are the type of like interesting little things to draw that I'm hoping you'll want to play with. Something like this is a little more appropriate than the animated rounded corner square, since you don't know how to deal with time and variables yet for assignment 1. That's coming very soon. But something like this would be achievable. It's just ellipses and scales and pops and pushes. And some colors that we threw in. You don't have to use variables for colors. You could just write them in manually. All right. So the updated slides are available on the website. I believe recording actually happened. Recording got corrupted from last class. I was very sad that the audio didn't work, but I'm pretty sure it's working this time because recording is still going. We have recording going for an hour and 11 minutes now, and it's actually capturing sound. So I think we're in good shape. So I'm not going to beleaguer this. I'm going to stop the recording.